Imagine a world where diamonds fall from the sky like rain. A planet where oceans of molten lava stretch as far as the eye can see. A strange sphere where you could float effortlessly above clouds made of ruby and sapphire crystals. These aren't scenes from science fiction or fantasy. They are real places that exist in the vast expanse of our universe, waiting to be explored by the curious mind. Welcome to Celestial Sleep, where we explore the wonders of the cosmos while helping you drift into peaceful slumber. I'm your guide on this journey through the stars, and tonight we'll be venturing beyond our solar system to discover some of the most bizarre, fascinating, and mind-bending exoplanets ever discovered. As you settle in and make yourself comfortable, allow your breathing to find a natural, gentle rhythm. Perhaps you're already lying down, your body supported and at ease. Or maybe you're preparing for sleep, knowing that soon you'll drift off to the gentle sounds of cosmic wonders. Wherever you are, whatever position brings you comfort, I invite you to join me on this journey of discovery and relaxation. The universe is vast beyond comprehension. In our Milky Way galaxy alone, scientists estimate there are over 100 billion stars. And orbiting these stars are countless planets, some familiar, some utterly alien to our understanding. For most of human history, we could only speculate about worlds beyond our solar system. But in recent decades, our technological capabilities have expanded dramatically, allowing us to detect and study these distant worlds. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995, a mere cosmic blink ago. Since then, we've identified thousands more, with new discoveries happening regularly. Each finding expands our understanding of what's possible in planetary formation and evolution. Each new world tells us something about the incredible diversity of our universe. Tonight, we'll explore the strangest of these worlds. Planets where the laws of physics create conditions so extreme, so unusual, that they challenge our imagination. Places where the familiar rules of our home planet no longer apply. Environments so alien that they seem to belong in dreams rather than reality. As we embark on this cosmic journey together, allow your mind to wander among the stars. Feel the gentle pull of curiosity, but also the soothing embrace of wonder. There's no need to remember every detail or fact. Simply let the cosmic narrative wash over you like gentle waves on a distant shore. Our journey begins now, as we leave Earth behind and venture into the depths of space, where strange worlds await our discovery. Before we explore specific exoplanets, let's take a moment to understand what these distant worlds are and how we find them. This foundation will help us appreciate just how remarkable our later discoveries truly are. Exoplanets, worlds that orbit stars other than our Sun, represent one of astronomy's most exciting frontiers. The term exo simply means outside, referring to their location beyond our own solar system. While humans have observed the planets in our solar system for thousands of years, exoplanets remained theoretical until relatively recently. The first confirmed detection came in 1992, when astronomers discovered planets orbiting a pulsar, the dense, spinning remnant of a massive star. Just 3 years later, in 1995, scientists confirmed the first exoplanet orbiting a main-sequence star similar to our Sun. This planet, called 51 Pegasi b, opened the floodgates to a new era of discovery. How do we find these distant worlds? Unlike the planets in our solar system, which we can observe directly through telescopes, most exoplanets are too far away and too faint compared to their host stars to be seen directly. Instead, astronomers have developed several ingenious methods to detect them indirectly. The most successful detection method is called the transit method. When a planet passes in front of its star from our perspective, it blocks a tiny portion of the star's light. By measuring this slight dimming repeated at regular intervals, scientists can confirm the presence of a planet and determine its size and orbit. Another approach is the radial velocity method, which detects the subtle wobble in a star's motion caused by the gravitational pull of an orbiting planet. As the planet orbits, it pulls the star slightly toward and away from Earth, creating tiny shifts in the star's light spectrum that we can measure. More recently, direct imaging has become possible for some larger planets that are farther from their stars. And microlensing, the bending of light by gravity, has revealed planets that might otherwise remain invisible to us. These detection methods each have their strengths and limitations. Transit observations favor large planets orbiting close to their stars. Radial velocity is more sensitive to massive planets. Direct imaging works best for young, hot planets far from their stars. This means our current census of exoplanets is incomplete, biased towards certain types of worlds that are easier to detect with our current technology. Yet even with these limitations, we've discovered over 5,000 confirmed exoplanets, with thousands more candidates awaiting verification. And among these thousands of worlds, we've found planets unlike anything in our solar system. Strange, extreme, and utterly fascinating environments that challenge our understanding of what's possible. The diversity of these worlds is staggering. Some exoplanets are so hot that their surfaces are molten. Others are perpetually shrouded in clouds. Some orbit their stars in just a few hours, while others take centuries to complete a single orbit. There are planets larger than Jupiter and others smaller than Mercury. Worlds with multiple suns in their skies and planets wandering through space without a star to call home. As we prepare to explore some of the strangest exoplanets ever discovered, remember that each represents a real place, a world that exists somewhere in the vastness of our galaxy. Though we may never visit these distant shores, the fact that we can know of their existence at all is one of humanity's greatest achievements. Our journey now takes us beyond the familiar, beyond the expected, to worlds so strange they seem to exist at the boundary between science and dreams. Let us begin our tour of the most bizarre exoplanets in our universe, starting with worlds of extreme temperature, places where heat and cold reach levels difficult to comprehend. Our first category of strange exoplanets takes us to worlds of temperature extremes, planets where heat and cold reach levels that would render Earth completely uninhabitable. These worlds exist at the boundaries of what we consider possible for planetary environments, yet they are very real, orbiting distant stars in our galaxy. Kelt 9b, the hottest known exoplanet. Our journey begins with Kelt 9b, a planet so hot it defies imagination. Discovered in 2017, this massive gas giant orbits its star at an incredibly close distance, so close that its year lasts just 1.5 Earth days. Its host star, Kelt 9, is an A-type star nearly twice as hot as our Sun, bathing the planet in intense radiation. The dayside temperature of Kelt 9b reaches approximately 4,600 degrees Kelvin. That's about 7,800 degrees Fahrenheit, or 4,300 degrees Celsius. This extreme heat makes Kelt 9b hotter than many stars. In fact, it's so hot that molecules cannot remain intact on its dayside. Elements we normally find as gases or solids exist there as atomic metals, vaporized by the incredible heat. Imagine a world where iron, titanium, and other metals float freely in the atmosphere as individual atoms, where the concept of clouds, oceans, or solid ground has no meaning. The atmosphere of Kelt 9b is constantly being stripped away by the intense stellar radiation, creating a comet-like tail of escaping gas that trails behind the planet as it orbits. Scientists believe that if Kelt 9b were any closer to its star, the planet would be completely torn apart by gravitational forces. It exists in a delicate balance, massive enough to hold itself together despite the extreme conditions, yet forever changed by its proximity to its stellar furnace. HD 80606b, the planet of extreme temperature swings. From constant heat, we move to a world of dramatic temperature changes. HD 80606b follows an extremely elongated, elliptical orbit around its star, similar to a comet rather than the nearly circular orbits of planets in our solar system. This unusual orbit creates something remarkable, the most extreme known weather variations of any exoplanet. For most of its 111-day orbit, HD 80,606b remains relatively distant from its star, with temperatures comparable to a hot day on Earth. But then, over a brief 20-hour period, the planet swings extremely close to its star in a cosmic dive that astronomers call periastron passage. During this close approach, the planet's temperature rises from about 80 degrees Celsius to over 1500 degrees Celsius, nearly a 1400-degree increase in less than a day. Imagine global temperatures rising from a warm summer day to far hotter than the melting point of silver in just hours. This temperature spike would create apocalyptic weather conditions. Massive storms would form instantly. The atmosphere would roil with turbulence. Any clouds present would vaporize in the sudden heat. And then, as the planet moves away from its star again, everything would gradually cool, only to repeat the cycle with the next orbit. HD 80,606b reminds us that planetary conditions need not be static. Some worlds experience climate variations far more extreme than anything in our solar system, creating environments that transform dramatically over time. WASP-12b, the planet being consumed by its star. Our next destination is perhaps one of the most doomed worlds ever discovered. WASP-12b is literally being torn apart by its star, its material streaming away to form a disk of gas around the star itself. This hot Jupiter orbits its star in just over one Earth day, maintaining an incredibly close distance of only about 2 million miles, a mere fraction of the distance between Mercury and our Sun. This proximity creates extreme tidal forces that have stretched the planet into an egg-like shape rather than a sphere. The temperature on WASP-12b reaches about 2500 degrees Celsius, causing its atmosphere to balloon outward. The star's gravitational pull is so strong that it overcomes the planet's gravity at the outer edges of this extended atmosphere, pulling material away from the planet. Astronomers estimate that WASP-12b is losing mass at a rate of about 6 billion metric tons per second. At this pace, the planet may be completely consumed within 10 million years, a cosmic blink of an eye. We are witnessing the slow death of a planet, a process that reminds us of the impermanence of even these massive celestial bodies. Ogle 2016 BLG 1195 LB, the frozen world. From scorching heat, we now travel to the opposite extreme, a world of perpetual ice and darkness. Ogle 2016 BLG 1195 LB is one of the coldest exoplanets ever discovered, with a surface temperature estimated to be around minus 220 degrees Celsius. This small, Earth-mass planet orbits a tiny red dwarf star so faint and small that it barely provides any warmth. The planet receives about as much energy from its star as Pluto does from our Sun, creating conditions where most gases would freeze solid. Discovered through a technique called gravitational microlensing, this distant world likely has a surface covered in frozen nitrogen, methane, and carbon dioxide, substances that exist as gases on Earth, but would be rock-hard solids in such extreme cold. If you could stand on the surface of this frozen world, properly protected from the killing cold, of course, you would see a sky dominated by stars. The host star would appear as little more than a bright point of light, providing minimal illumination to the icy landscape. Any atmosphere would have long ago frozen and fallen to the surface as exotic snow. In such extreme cold, movement would be difficult. Materials we consider flexible on Earth would become brittle. Water ice would be as hard as steel. The very air, if any remained, would be still, as there would be little energy to drive weather patterns. It is a world of cosmic winter, eternal and unchanging. 55 Cancri E. The Diamond Planet. Our final extreme temperature world is perhaps the most valuable planet ever discovered, if one could somehow mine it. 55 Cancri E, also known as Janssen, is thought to be composed largely of carbon, much of it potentially in the form of diamond. This super-Earth orbits extremely close to its star, completing an orbit in just 18 hours. Its surface temperature is estimated to be around 2700 degrees Celsius, hot enough to melt most rocks. But carbon behaves differently under extreme pressure and temperature. Scientists believe that the interior of 55 Cancri e may contain significant amounts of diamond, perhaps equivalent to 3 Earth masses of this precious material. Under the immense pressure of the planet's gravity and the extreme heat from its star, carbon atoms would arrange themselves into the crystalline structure we know as diamond. Imagine a world where mountains could be made of diamond, where the very bedrock sparkles with crystalline carbon. The surface might feature oceans of liquid carbon compounds, perhaps with diamond icebergs floating upon them. The atmosphere, rich in carbon dioxide and more exotic compounds, would be thick and hot, creating a pressure cooker environment unlike anything in our solar system. Of course, no human could ever visit such a world. The heat alone would vaporize any spacecraft that attempted to land. The crushing gravity, about twice Earth's, combined with the extreme temperature and pressure, would make exploration impossible with any technology we can currently imagine. Yet it exists, a diamond world circling its star every 18 hours, a testament to the incredible diversity of planetary formation in our universe. As we leave these worlds of temperature extremes behind, remember that each represents a real place, a destination that exists somewhere in the vastness of space, following the same physical laws that govern our own world, yet producing results beyond our everyday experience. Now let us drift to our next category of strange worlds, planets with bizarre atmospheres that create some of the most alien environments ever discovered. Our journey continues as we explore planets with some of the most unusual atmospheres ever discovered. These worlds feature weather patterns and atmospheric compositions that challenge our understanding of planetary science and create conditions that seem pulled from the pages of science fiction. HD 180-9733b, the planet where it rains glass sideways. Our first atmospheric wonder is HD 180-9733b, a hot Jupiter located about 63 light-years from Earth. From a distance, this world might appear deceptively peaceful, its deep blue color reminiscent of Earth's oceans. But this azure hue doesn't come from water. Instead, it's the result of light scattering through an atmosphere filled with silicate particles, essentially tiny bits of glass. HD 180-9733b orbits extremely close to its star, completing an orbit in just 2.2 Earth days. This proximity creates ferocious weather conditions. The planet is tidally locked, meaning one side always faces its star while the other remains in perpetual darkness. This creates an extreme temperature difference between the day side and night side, generating winds that reach speeds of over 5,400 miles per hour, 7 times the speed of sound on Earth. In this violent atmosphere, silicate particles, the main component of glass, condense in the upper atmosphere and are carried by supersonic winds. As these particles rain down, they don't fall vertically as rain does on Earth. Instead, they're swept horizontally at incredible speeds, creating what scientists describe as sideways rain made of molten glass shards. Imagine standing on this world, protected somehow from its killing heat and crushing pressure. You would witness a sky filled with blue haze, streaked with glass rain moving horizontally across your field of vision. The constant roar of supersonic winds would be deafening. The heat would be unbearable. Yet this is the daily reality on HD 180-9733b, a world where weather takes on forms we can barely comprehend. Kepler 7b, the world of shimmering clouds. From glass rain, we drift to a world of perpetual shimmering clouds. Kepler 7b is one of the most reflective planets ever discovered, with an albedo reflectivity higher than that of Venus, which is the most reflective planet in our solar system. This hot Jupiter is about half the mass of Jupiter, but is nearly 50% larger in radius, making it one of the least dense planets known, with a density similar to styrofoam. Scientists believe this low density is partly due to its proximity to its star, which causes the planet's atmosphere to puff up and extend outward. What makes Kepler-7b truly remarkable is its cloud cover. The western hemisphere of the planet is dominated by high, reflective clouds that scientists believe are composed of exotic materials. Unlike Earth's water-based clouds, these may contain particles of corundum, the same mineral that forms rubies and sapphires, or other exotic compounds that can remain stable at the planet's scorching temperature of about 1400 degrees Celsius. These jewel-like clouds would create a spectacular sight, reflecting starlight with a shimmering, possibly iridescent quality. The eastern hemisphere, by contrast, appears to have fewer clouds, creating a stark division between the two sides of the planet. The clouds on Kepler-7b don't seem to follow the expected patterns based on the planet's temperature. They appear in unexpected locations and remain more stable than models predict. This suggests atmospheric circulation patterns unlike anything in our solar system, another reminder of how diverse planetary conditions can be. GJ1214b. The water world with a steamy atmosphere. Our next destination takes us to a very different kind of world, a potential water world enshrouded in thick, steamy atmosphere. GJ1214b orbits a red dwarf star about 40 light-years from Earth and represents one of the most intriguing super-Earths discovered to date. With a radius about 2.7 times that of Earth and a mass about 6.5 times greater, GJ1214b falls into the category of planets with no equivalent in our solar system. Its density is too low to be composed primarily of rock like Earth, yet too high to be a gas giant like Neptune. The most likely explanation is that a significant portion of its mass consists of water. Scientists believe GJ1214b may have a rocky core surrounded by a deep ocean that transitions gradually into its thick atmosphere without a clear boundary, a true water world. But this is no Earth-like ocean. The temperature of GJ1214b is estimated to be around 200 degrees Celsius. At this temperature, the atmosphere would contain substantial amounts of water vapor. But the pressure created by this thick atmosphere would prevent the ocean below from boiling away entirely, creating an environment that exists in a state between liquid and gas, a supercritical fluid where the distinction between ocean and atmosphere blurs. If you could somehow observe this world up close, you might see an endless expanse of dark ocean beneath a thick, steamy haze. The water would not be blue like Earth's oceans, but darker, perhaps with exotic compounds dissolved within it. The sky would be perpetually cloudy, with little direct starlight reaching the surface. It would be a world of eternal twilight, hot and humid, beyond anything experienced on Earth. Recent observations suggest the atmosphere may also contain significant amounts of methane and carbon compounds, creating a greenhouse effect that traps heat and further warms the planet. This combination of water, heat, and organic compounds raises intriguing questions about the potential for chemical processes that might, under the right conditions, lead to interesting prebiotic chemistry. HAT P7b. The planet with ruby and sapphire clouds. Our exploration of bizarre atmospheres continues with HAT P7b, a hot Jupiter located about 1,000 light-years from Earth. This world experiences some of the most exotic weather ever discovered, clouds that may be composed of corundum, the mineral that forms rubies and sapphires on Earth. HAT P7b orbits its star at an extremely close distance, completing an orbit in just 2.2 Earth days. It is tidally locked, with one side eternally facing its star. The dayside temperature reaches about 2,600 degrees Celsius, hot enough to vaporize most minerals. But as this superheated gas moves to the cooler night side, certain minerals can condense to form clouds. Observations from NASA's Kepler Space Telescope revealed something remarkable about HAT P7b. Its brightest point shifts position. Sometimes the brightest region is directly under its star, as expected. But at other times, the brightest point appears offset, suggesting the presence of massive, reflective cloud formations that form and dissipate in cycles. Based on the temperature and composition of the planet, scientists believe these clouds may contain aluminum oxide, the same compound that forms rubies and sapphires when trace elements are present. Imagine clouds of tiny gemstones forming on the night side of the planet where temperatures are cool enough for these minerals to condense, then being carried by winds to the day side where they vaporize again in the intense heat. The result would be a constant cycle of gemstone rain, vaporization, and cloud formation, a weather pattern unlike anything in our solar system. The visual effect would be stunning. Clouds that shimmer with the red and blue hues of rubies and sapphires, constantly forming and dissipating against the backdrop of a scorching hot planet. WASP 76b, the Iron Rain planet. Our final atmospheric wonder is perhaps the most dramatic, a world where it literally rains molten iron. WASP 76b, located about 640 light-years away, presents one of the most extreme weather phenomena ever discovered. Like many hot Jupiters, WASP 76b is tidally locked, with one side perpetually facing its star. The dayside temperature reaches an incredible 2400 degrees Celsius, hot enough to vaporize metals like iron. This iron vapor is carried by strong winds to the night side of the planet, where temperatures are only about 1500 degrees Celsius. This temperature difference is enough to allow the iron vapor to condense into liquid droplets, creating iron rain that falls through the planet's atmosphere. Imagine standing at the boundary between day and night on this world, if such a thing were possible, and watching as iron literally precipitated from the sky, falling as glowing, molten droplets. The discovery of iron rain on WASP 76b was made possible by the espresso instrument on the Very Large Telescope in Chile, which detected iron absorption in the evening region of the planet, but not in the morning region, evidence that the iron was condensing and falling out of the atmosphere during the night. This extreme weather cycle, vaporization on the day side, condensation and precipitation on the night side, creates a perpetual cycle of metallic rain, unlike anything we experience on Earth. It's a reminder of how the same physical laws that create gentle water rain on our world can, under different conditions, produce phenomena that seem almost magical in their strangeness. As we leave these worlds of bizarre atmospheres behind, take a moment to appreciate the incredible diversity of planetary environments. The same basic elements that make up our own world, hydrogen, oxygen, carbon, silicon, iron, can, under different conditions, create places so alien they challenge our imagination. Now, let us drift toward our next category of strange worlds. Planets, with compositions so unusual they defy our expectations of what a planet can be. Our cosmic journey now takes us to planets with compositions so unusual they challenge our understanding of planetary formation. These strange worlds are made of materials or have structures that we don't see in our own solar system, revealing the incredible diversity of planetary bodies throughout the universe. PSRB 1257 plus 12b, C, and D. The pulsar planets. Our first unusual worlds are also historically significant. They were the first confirmed exoplanets ever discovered. What makes these planets truly strange is not their composition, but rather the star they orbit. PSRB 1257 plus 12 is not a normal star, but a pulsar, the rapidly rotating remnant of a massive star that exploded as a supernova. Pulsars are among the most extreme objects in the universe. They spin incredibly fast, emitting beams of radiation that sweep across space like cosmic lighthouses. PSRB 1257 plus 12 rotates about 161 times per second, bathing its planets in intense radiation with each rotation. The discovery of planets around this pulsar in 1992 was completely unexpected. Scientists had assumed that the violent supernova explosion that created the pulsar would have destroyed any planets in the system. Yet there they were, 3 worlds orbiting the stellar remnant. The planets, named PSRB 1257 plus 12b, C, and D, are thought to be composed primarily of rock and metals. But unlike the rocky planets in our solar system, these worlds formed after the death of their star. Scientists believe they coalesced from the debris left over from the supernova explosion, making them fundamentally different from Earth or Mars. If you could somehow visit these worlds, protected from the deadly radiation, of course, you would witness a sky dominated not by the warm glow of a sun, but by the eerie, rhythmic flashing of the pulsar. Every few milliseconds, a beam of intense radiation would sweep across the landscape, like a cosmic strobe light pulsing in perfect regularity. Between these flashes, the world would be illuminated only by distant stars. The surface of these planets would likely be barren and lifeless, baked by radiation and composed of materials forged in the heart of a dying star. They are worlds born from cosmic catastrophe, a reminder that even in the aftermath of stellar death, new planetary systems can emerge. J1407b, the Super Saturn. From planets orbiting a dead star, we move to a world with the most spectacular ring system ever discovered. J1407b, sometimes called Super Saturn, orbits a young star about 434 light-years from Earth. What makes this planet extraordinary is its ring system, which is approximately 200 times larger than Saturn's rings. The rings of J1407b extend about 90 million miles from the planet, a distance roughly equivalent to the space between Earth and our Sun. If Saturn had rings this large, they would dominate Earth's night sky, appearing many times larger than the full moon. Scientists discovered this massive ring system when they observed the young star J1407 dimming in an unusual pattern. The light curve suggested an enormous structure of rings with gaps, similar to Saturn's, but on a much grander scale. The entire ring system contains roughly the mass of Earth, composed primarily of dust and ice particles. The rings likely represent a planetary system in the process of formation. Within these vast rings, moons may be forming, gradually clearing gaps in the ring material as they sweep up debris. We may be witnessing the birth of an entire moon system around this giant planet. Imagine viewing this world from a distance, a massive planet surrounded by concentric rings stretching outward for millions of miles, catching and reflecting the light of its star. The rings would not appear uniform but would show variations in thickness and density, with gaps where moons are forming or already exist. Kepler-10c, the mega-Earth. Our next destination challenges our understanding of what a rocky planet can be. Kepler-10c, located about 560 light-years away, is a world that shouldn't exist according to our previous models of planetary formation. With a diameter about 2.3 times that of Earth, but a mass 17 times greater, Kepler-10c is extraordinarily dense for its size. Scientists had thought that planets of this mass would inevitably gather large hydrogen-helium atmospheres during formation, becoming gas giants like Neptune. Yet Kepler-10c appears to be solid, a massive rocky world unlike anything in our solar system. This discovery forced astronomers to reconsider their models of planetary formation. Somehow, this world formed without accumulating the thick atmosphere we would expect for a planet of its mass. Perhaps it formed very late in its solar system's development, after much of the gas had dissipated. Or perhaps its atmosphere was stripped away by intense radiation from its star. Standing on the surface of Kepler-10c would be a crushing experience, literally. The surface gravity would be roughly 3 times stronger than Earth's. A person who weighs 150 pounds on Earth would feel like they weighed 450 pounds on this mega-Earth. Every movement would require enormous effort. Simply standing would be exhausting. The composition of this world is likely similar to Earth's silicate rocks and metals, but compressed under enormous pressure. The interior structure might include exotic forms of familiar materials, their molecular and crystal structures altered by the intense pressure. It's a world of extremes, showing us that rocky planets can grow far larger than we previously thought possible. GJ436b, the ice giant that shouldn't exist. From a world that's unexpectedly solid, we move to one that's unexpectedly hot, yet still maintains its ice. GJ436b is a Neptune-sized exoplanet located about 33 light-years from Earth. What makes this world bizarre is that despite orbiting very close to its star, with a surface temperature of about 800 degrees Fahrenheit, 427 degrees Celsius, it appears to be composed largely of hot ice. This seeming contradiction, ice existing at temperatures far above its normal melting point, is possible because of the extreme pressure in the planet's interior. Under tremendous pressure, water molecules arrange themselves into a crystal structure called Ice X that remains solid despite the high temperature. This exotic form of water is not found naturally on Earth. It exists in a state called superionic, where oxygen atoms form a crystal lattice, while hydrogen atoms flow freely like a liquid through this lattice. It's neither truly solid nor truly liquid in the conventional sense. GJ 436 b likely has a rocky core surrounded by a thick layer of this exotic hot ice, which in turn may be covered by a hydrogen-rich atmosphere. The planet also appears to be losing its atmosphere at a remarkable rate, with hydrogen streaming away to form a comet-like tail behind it as it orbits its star. TOI 849b. The exposed planetary core. Our final strange composition world may be one of the most unusual yet, a planet that appears to be nothing but a naked core. TOI 849b, discovered in 2020, orbits its star every 18 hours at a distance so close that its surface temperature reaches about 1800 degrees Celsius. What makes TOI 849b remarkable is its density. Despite being similar in size to Neptune, it has a mass about 40 times that of Earth, making it extraordinarily dense. The most likely explanation is that we're observing the exposed core of a gas giant, a world that either lost its gaseous envelope or never fully developed one. Scientists have two theories for how this strange world came to be. Perhaps it was once a Jupiter-like planet whose outer layers were stripped away by intense stellar radiation or a catastrophic collision. Or perhaps it's a failed gas giant, a planetary core that formed too late in its solar system's development to accumulate the hydrogen and helium needed to grow into a conventional gas giant. Either way, TOI 849b offers a unique opportunity to study something we can never observe in our own solar system, the core of a giant planet. Its composition is likely rich in heavy elements like iron, magnesium, silicon, and perhaps even more exotic materials formed under extreme pressure. If you could somehow visit this world, protected from its killing heat and crushing gravity, you would stand directly on the material that normally forms the hidden heart of a giant planet. The landscape would be unlike anything in our solar system, composed of dense, exotic minerals forged under pressures millions of times greater than Earth's atmosphere. TOI 849b reminds us that planetary systems are dynamic places, where catastrophic events can transform worlds completely. What we observe today may be just one phase in a long and violent planetary history. With past configurations, we can only infer from the clues left behind. As we leave these worlds of strange composition, consider how the basic building blocks of planets, rock, ice, gas, and metal, can combine in such diverse ways across the universe. The same elements that make up our familiar Earth can, under different conditions and histories, create worlds that seem almost unimaginable. Now, let us drift toward our next category of cosmic oddities, planets with unusual orbits and rotations that create some of the strangest days and years in the universe. Our cosmic journey now takes us to worlds with some of the most unusual orbital and rotational characteristics ever discovered. These planets challenge our understanding of how solar systems form and evolve, with orbits and days unlike anything we experience in our own solar system. Kepler 16b, the Tatooine planet. Our first unusual world is one that seems pulled from science fiction, a planet with two suns. Kepler 16b orbits a binary star system about 200 light-years from Earth, much like the fictional planet Tatooine from Star Wars. This circumbinary planet orbits both stars as they orbit each other, creating a cosmic dance of extraordinary complexity. Kepler 16b is a cold world, roughly the size of Saturn, composed primarily of gas with a solid core. Its average temperature is about -100 degrees Celsius, far too cold for liquid water. But what makes this world truly remarkable is its sky. From the surface, or rather, from the top of its thick atmosphere, an observer would witness two suns rising and setting in complex patterns. The two stars in the Kepler-16 system are quite different from each other. The primary star is about 69% the mass of our Sun, while its companion is just 20% as massive. They orbit each other every 41 days, sometimes appearing close together in the sky, other times on opposite sides of the horizon. This binary dance would create a constantly changing pattern of light and shadow on Kepler-16b. Sometimes both stars would be visible, casting double shadows across the landscape. At other times, one star might set while the other remains above the horizon. Eclipses would occur regularly as the stars pass in front of each other from the planet's perspective. The seasons on such a world would be extraordinarily complex, with temperature patterns determined not just by the planet's orbit, but by the changing positions of both stars. It's a reminder that what we consider normal for a planetary system, a single star with planets in relatively stable orbits, is just one possibility among many. HD 80606b. The comet-like planet. We briefly encountered HD 80606b earlier when discussing temperature extremes. But this world deserves special attention for its highly eccentric orbit. Most planets in our solar system follow nearly circular paths around the Sun. HD 80606b, by contrast, follows an orbit more like that of a comet, extremely elongated and elliptical. The eccentricity of HD 80606b's orbit is about 0.93, among the highest known for any planet. At its farthest point from its star, it's about as distant as Venus is from our Sun. But at its closest approach, it dives to just 3% of that distance, closer than Mercury's orbit. This extreme orbit creates dramatic changes in the planet's environment. For most of its 111-day orbit, HD 80606b is a relatively cool gas giant. But during its brief close approach to its star, it experiences a blast of heat that raises its temperature by over 1,400 degrees Celsius in less than a day. Scientists believe this unusual orbit may have been caused by gravitational interactions with another planet, or perhaps a passing star early in the system's history. Whatever the cause, the result is a world that experiences conditions unlike any planet in our solar system, alternating between relative calm and extreme, short-lived heat. If you could somehow observe this planet over time, you would see it spending most of its orbit moving relatively slowly through the outer reaches of its solar system. Then, as it begins to fall toward its star, it would accelerate dramatically, whipping around the star in a brief, violent periastron passage before being flung outward again to begin the cycle anew. PSRJ 1719 to 1438b. The diamond planet in a millisecond. Our next destination is another world orbiting a pulsar, but with characteristics even more extreme than the pulsar planets we discussed earlier. PSRJ 1719 to 1438b orbits its pulsar every 2.2 hours, an incredibly short year. That places it extremely close to its host star. This proximity would be impossible around a normal star, as the planet would be torn apart by gravity or consumed by stellar material. But pulsars are incredibly dense and compact. This one packs more mass than our Sun into a sphere, just 20 kilometers in diameter. What makes PSRJ 1719 to 1438 be truly bizarre is its likely composition. Scientists believe it is the remnant core of a white dwarf star that has been stripped of its outer layers, leaving behind primarily carbon and oxygen under enormous pressure. Under these conditions, the carbon would crystallize into diamond. This diamond planet is about the size of Jupiter, but contains at least as much mass as our Sun. The density is almost unimaginable. A cubic centimeter of this material would weigh thousands of kilograms on Earth. It's a world of superlatives, one of the densest planets known, with one of the shortest orbital periods, circling one of the most extreme types of stellar objects. The environment around this planet would be unlike anything in our experience. The pulsar emits intense beams of radiation that sweep across space like a lighthouse beam, pulsing with perfect regularity many times per second. The planet itself, a massive diamond sphere, would reflect this radiation in rhythmic flashes as it completes an orbit in just over 2 hours. WASP-12b, the egg-shaped world. We briefly encountered WASP-12b earlier when discussing extreme temperature worlds. But this planet deserves special attention for its unusual shape. Most planets are roughly spherical, pulled into a ball by their own gravity. WASP-12b, however, has been stretched by tidal forces into an egg-like shape. This hot Jupiter orbits so close to its star that it completes an orbit in just over 1 Earth day. At this distance, the star's gravitational pull is dramatically stronger on the side of the planet facing the star than on the far side. This differential pull stretches the planet along the star-planet axis, creating an elongated, egg-like shape. The deformation is substantial. The planet is about 1.4 times wider along its longest axis than along its shortest. This stretching generates enormous tidal heating within the planet, contributing to its already extreme temperature of about 2,500 degrees Celsius. WASP-12b is so close to its star that it fills a significant fraction of its Roche lobe, the region within which material is gravitationally bound to the planet. Material at the outer edges of the planet's extended atmosphere can escape this gravitational bond and be pulled toward the star, creating a steady stream of planetary material flowing from the planet to its star. WASP-17b, the retrograde planet. Our next unusual world challenges one of the most fundamental patterns in our solar system. In our cosmic neighborhood, all the planets orbit the Sun in the same direction that the Sun rotates, a pattern thought to result from the way solar systems form from spinning disks of gas and dust. But WASP-17b breaks this rule completely. WASP-17b orbits its star in the opposite direction of the star's rotation, what astronomers call a retrograde orbit. This massive gas giant, located about 1,000 light-years from Earth, is also one of the least dense planets known, with a density less than 1/5 that of Jupiter. Scientists believe the retrograde orbit may be the result of a dramatic event in the planet's history, perhaps a close encounter with another planet that flipped its orbital direction, or even a collision that reversed its course. Whatever the cause, WASP-17b travels a path contrary to what we would expect from standard models of planetary formation. The retrograde orbit has consequences for the planet's evolution. The opposing motions of the planet and the star's rotation create complex tidal interactions that may contribute to the planet's inflated size and low density. It's a reminder that planetary systems can experience dramatic, system-altering events long after their initial formation. 2 Mass J2126 to 8140, the planet with the widest known orbit. Our final unusual orbit belongs to a world that challenges our definition of a planetary system. 2 Mass J2126 to 8140 is a gas giant about 12 to 15 times the mass of Jupiter, orbiting its star at the staggering distance of about 7,000 astronomical units. 1 astronomical unit is the distance between Earth and the Sun. This enormous separation means the planet takes roughly 1 million years to complete a single orbit around its star. For comparison, Pluto, the most distant major body in our solar system, orbits at just 40 astronomical units and completes an orbit in 248 years. The distance between 2 Mass J2126 to 8140 and its star is so vast that for many years, astronomers didn't even realize they were connected. The planet was thought to be a rogue world drifting through space without a star. Only careful measurements of both objects' movements through the galaxy revealed their gravitational relationship. At such an extreme distance, the star would appear as little more than a very bright point of light in the planet's sky, providing minimal heat or illumination. The planet itself is relatively young, about 10 to 45 million years old, and still glowing from the heat of its formation. This internal heat, rather than stellar radiation, is likely the dominant source of energy for this distant world. The discovery of 2-mass J2126 to 8140 expands our understanding of how far planetary systems can extend and challenges us to reconsider what constitutes a star-planet relationship. It exists in a gray area between a traditional planetary system and two independent objects merely passing through space in a loosely bound dance that will last billions of years. As we leave these worlds of unusual orbits and rotations, consider how the basic forces of gravity and momentum can create such diverse planetary systems across our galaxy. The same physical laws that govern our own solar system can, under different initial conditions, produce worlds with days, years, and seasons that defy our expectations. Now, let us drift toward our final category of strange worlds, potentially habitable planets with characteristics so unusual they challenge our understanding of where life might exist in the universe. Our final journey takes us to perhaps the most intriguing category of strange exoplanets, worlds that, despite their alien characteristics, might potentially support some form of life. These planets challenge our understanding of habitability and expand our search for environments where life might exist beyond Earth. Proxima Centauri b, our nearest potentially habitable neighbor. Our first potentially habitable strange world is also the closest known exoplanet to Earth. Proxima Centauri b orbits the red dwarf star Proxima Centauri, just 4.2 light-years from our solar system, a cosmic stone's throw away. This proximity makes it not only an object of scientific interest, but also a potential target for future interstellar missions. Proxima Centauri b is about 1.3 times the mass of Earth and orbits within its star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. But this world is far from an Earth twin. Its star, Proxima Centauri, is much smaller and cooler than our Sun, emitting primarily red and infrared light rather than the full spectrum we receive on Earth. The planet completes an orbit in just 11.2 Earth days, placing it much closer to its star than Earth is to the Sun. At this proximity, Proxima Centauri b is almost certainly tidally locked, with one side perpetually facing its star, while the other remains in eternal darkness. This tidal locking creates an environment unlike anything in our solar system, a world divided between permanent day and permanent night. The day side might be too hot for liquid water, while the night side might be frozen. But in the boundary region between light and shadow, what astronomers call the terminator line, temperatures could be moderate enough for liquid water and potentially life. Another challenge for habitability is Proxima Centauri itself. Red dwarf stars are known for powerful flares that emit intense ultraviolet and X-ray radiation. These flares, far more powerful relative to the star's size than our Sun's, could strip away the planet's atmosphere over time or bathe its surface in sterilizing radiation. Yet despite these challenges, Proxima Centauri b remains one of our most intriguing targets in the search for habitable worlds. If the planet has a strong magnetic field, it might shield its surface from stellar radiation. If it has a thick atmosphere, heat could be distributed from the day side to the night side, creating a more uniform climate. And if it has substantial oceans, these could moderate temperature extremes and provide environments where life might evolve. Imagine standing on the terminator line of this world, where perpetual dawn or dusk would paint the landscape in eternal twilight. In one direction, the red dwarf star would hang motionless in the sky, casting everything in a reddish hue. In the other direction would be perpetual night, perhaps with auroras dancing across the sky as charged particles from stellar flares interact with the planet's magnetic field. TRAPPIST-1e. A world in a compact system, our next potentially habitable strange world is part of one of the most remarkable planetary systems ever discovered. TRAPPIST-1e is one of 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1, about 40 light-years from Earth. What makes the TRAPPIST-1 system so unusual is its compact nature. All 7 planets orbit closer to their star than Mercury orbits our Sun. Yet because TRAPPIST-1 is so much cooler than our Sun, 3 of these worlds, planets E, F, and G, orbit within the star's habitable zone. Of these, TRAPPIST-1e is considered the most promising for habitability. It's slightly smaller than Earth, with about 77% of our planet's mass, and receives a similar amount of total radiation from its star as Earth does from the Sun. Like Proxima Centauri b, TRAPPIST-1e is likely tidally locked, creating the same division between permanent day and night. But what makes this world particularly interesting is its relationship with the other planets in the system. The 7 planets of TRAPPIST-1 orbit in a resonant chain, with their orbital periods forming simple numerical ratios with each other. This complex gravitational dance would create spectacular celestial displays. From the surface of TRAPPIST-1e, the other planets would appear as large disks in the sky, sometimes passing in front of the star to create frequent eclipses. These gravitational interactions would also generate tidal heating within the planet, the same process that keeps the interior of Jupiter's moon Io molten and volcanically active. This additional heat source could help maintain a warmer climate and potentially drive geological activity important for long-term habitability. Recent studies suggest TRAPPIST-1e may have a predominantly rocky composition similar to Earth, possibly with a thin atmosphere and maybe even liquid water on its surface. The planet's density indicates it could have significant amounts of water, perhaps as much as 5% of its mass, compared to less than 0.1% for Earth. Imagine a world where the sky is dominated not just by a reddish star, but by the disks of neighboring planets, sometimes appearing several times larger than our moon appears from Earth, where days and nights don't cycle but remain fixed to specific regions, where tidal forces from neighboring worlds might drive geological activity, perhaps creating mountain ranges or volcanic features unlike anything on Earth. Kepler 442b, the most Earth-like exoplanet. From worlds orbiting dim red dwarfs, we move to a planet that might be the most similar to Earth yet discovered, at least in terms of the light it receives. Kepler 442b orbits a K-type orange dwarf star about 1,200 light-years from Earth, with a radius about 1.3 times that of Earth, and receiving about 70% of the light that Earth does from the Sun. Kepler 442b has one of the highest Earth Similarity Index values of any known exoplanet. Its star, while cooler and smaller than our Sun, is more stable than the red dwarfs we've discussed previously, emitting fewer potentially harmful flares. Kepler 442b takes 112 Earth days to complete an orbit, placing it firmly within its star's habitable zone. Unlike the tidally locked worlds orbiting red dwarfs, this planet might rotate independently of its orbit, creating a day-night cycle similar to Earth's, though likely of different duration. The light on Kepler 442b would appear different from what we experience on Earth. Its orange dwarf star would bathe the landscape in a warm, amber glow rather than the white-yellow light of our Sun. Plant life, if it exists, might evolve different pigments for photosynthesis, potentially creating forests of black or purple rather than green. While we know little about this world's atmosphere or surface conditions, its position in the habitable zone of a relatively stable star makes it one of our best candidates for a truly Earth-like environment elsewhere in the galaxy. Imagine walking on a world where the sunlight carries an amber hue, where the days might last longer than on Earth, where the night sky would reveal unfamiliar constellations. The gravity would be somewhat stronger than Earth's, making objects feel heavier and perhaps influencing the evolution of any life that might exist there. Kepler 186f, the first Earth-sized planet in a habitable zone. Our exploration continues with Kepler 186f, a world that made history as the first Earth-sized planet discovered orbiting within its star's habitable zone. Located about 500 light-years from Earth, This planet orbits a red dwarf star significantly cooler and smaller than our Sun. Kepler 186f is just 10% larger than Earth in diameter, making it a true Earth-sized world rather than a super-Earth. It receives about 32% of the light that Earth does from the Sun, placing it toward the outer edge of its star's habitable zone, similar to Mars in our solar system. The planet completes an orbit every 130 Earth days. At this distance from its star, Kepler 186f might avoid being tidally locked, potentially allowing for a day-night cycle. However, its rotation period remains unknown. The light on Kepler 186f would appear quite different from Earth. Its red dwarf star would cast a dimmer, redder light across the landscape. Noon on Kepler 186f might appear no brighter than an hour before sunset on Earth, with everything illuminated in reddish hues. If photosynthetic life were to evolve on such a world, it would need to adapt to this different light spectrum. Plants might be black instead of green to absorb as much of the available light as possible. The dimmer illumination might also lead to larger leaves or other adaptations to capture sufficient energy. The climate of Kepler 186f would depend greatly on its atmosphere. With less stellar energy reaching its surface, the planet would need a stronger greenhouse effect than Earth to maintain temperatures suitable for liquid water. A thicker atmosphere rich in carbon dioxide or other greenhouse gases might provide this warming effect. Imagine a world where the midday sun appears as dim as Earth's late afternoon, where the light carries a perpetual sunset quality, where plants, if they exist, might be dark purple or black rather than green. The night would be darker still, with stars appearing more brilliant against the blackness of space due to the dimmer competing light from the planet's star during the day. TOI 700d, a world around a quiet red dwarf. Our final potentially habitable strange world orbits one of the quieter red dwarf stars known. TOI 700d is an Earth-sized planet orbiting within the habitable zone of its star, located about 100 light-years from our solar system. What makes TOI 700d particularly interesting is its star. Unlike many red dwarfs, TOI 700 appears to be relatively quiet, with fewer of the powerful flares that could strip away planetary atmospheres or bathe surfaces in harmful radiation. This stellar calm improves the prospects for long-term habitability. The planet is about 20% larger than Earth and completes an orbit every 37 days. At this distance from its star, TOI 700d is almost certainly tidally locked, with one side in perpetual daylight and the other in eternal night. Recent modeling suggests TOI 700d could support a range of possible climates, depending on its atmospheric composition. Some models show it could maintain surface temperatures suitable for liquid water across significant portions of its surface, particularly in the twilight zone between its day and night sides. One intriguing possibility is that if the planet has oceans, global circulation patterns could distribute heat from the day side to the night side, potentially creating a band of habitability that encircles the entire planet along the Terminator line. Imagine standing in this twilight zone, where the red dwarf star would hang motionless at the horizon, neither rising nor setting. In one direction would be the perpetually lit day side, perhaps with clouds forming over warmer regions and flowing toward the cooler night. In the other direction would be the eternal night, perhaps with ice sheets extending from the coldest regions of the dark side. As we conclude our tour of potentially habitable strange worlds, remember that habitability exists on a spectrum. Some of these planets might be completely inhospitable despite their promising characteristics. Others might harbor simple microbial life. And perhaps, just perhaps, one or more might support complex ecosystems unlike anything we've imagined. The diversity of these potentially habitable worlds reminds us that life, if it exists beyond Earth, might adapt to conditions very different from those we experience. The search for life beyond our solar system is, in many ways, a search for the limits of life itself. an exploration of how adaptable and resilient biology can be when faced with environments both familiar and utterly alien. As we leave these strange worlds behind and prepare to conclude our cosmic journey, take a moment to appreciate the incredible diversity of planets that exist in our galaxy. From scorching hot worlds where it rains molten iron to potentially habitable planets with eternal twilight, the universe has created environments that challenge our imagination and expand our understanding of what's possible. As our journey through the strange worlds beyond our solar system comes to a close, let us take a moment to reflect on what we've discovered together. We've traveled to planets of extreme temperatures, where metals vaporize in the atmosphere or freeze into exotic forms of ice. We've visited worlds with bizarre atmospheres, where it rains molten glass sideways or iron falls from the sky. We've explored planets with compositions unlike anything in our solar system, and orbits that challenge our understanding of how planetary systems form and evolve. In all this cosmic diversity, we find a profound truth. The universe is far more creative and varied than we could have imagined. The same basic elements, hydrogen, oxygen, carbon, silicon, iron, that make up our familiar Earth can, under different conditions, create worlds that seem to exist at the boundary between science and dreams. As you drift towards sleep, perhaps your mind is still wandering among these strange worlds. Maybe you're imagining the diamond mountains of 55 Cancri E, or the ruby clouds of Hat P7b, or the eternal twilight of Proxima Centauri b. These journeys of imagination connect us to the cosmos in a deeply personal way, reminding us that we are made of the same star-forged elements as these distant worlds. The exploration of exoplanets is still in its infancy. Each year brings new discoveries, new strange worlds to contemplate. What we know today is just the beginning of a much longer journey of discovery that will continue long after we're gone. Future generations will look back at this time as the dawn of exoplanet astronomy, when humans first began to truly understand the incredible diversity of worlds that exist among the stars. There is something profoundly humbling about knowing that as you lie here, preparing for sleep, trillions of miles away these strange worlds continue their orbits around distant stars. The diamond planet still sparkles. The iron rain still falls. The binary sunsets still paint alien landscapes in double shadows. They exist whether we observe them or not, a reminder of how vast and wondrous our universe truly is. Perhaps the most remarkable thing about our journey is not the strange worlds themselves, but the fact that we can know of their existence at all. Through ingenuity, persistence, and collaboration, humans have developed the technology and knowledge to detect and study planets orbiting stars so distant that they appear as mere points of light in our most powerful telescopes. It is one of humanity's greatest intellectual achievements. As your consciousness begins to drift, like a spacecraft on a long journey between the stars, remember that you too are part of this cosmic story. The atoms in your body were forged in ancient stars that exploded billions of years ago, scattering their elements across space to eventually become part of our world and part of you. We are, in the most literal sense, made of stardust, connected to these strange, distant worlds by our shared cosmic origin. May your dreams tonight be filled with cosmic wonders. Perhaps you'll visit worlds we've discussed, or imagine new ones yet to be discovered. As you float in that space between wakefulness and sleep, remember that the boundary between imagination and reality is not always clear. The universe has proven time and again to be more strange and wonderful than we could have predicted. Extreme temperature worlds. Kelt 1b, the brown dwarf borderline. Our exploration of extreme temperature worlds continues with Kelt 1b, a fascinating object that exists at the boundary between planet and star. Located approximately 725 light-years from Earth, Kelt 1b is classified as a brown dwarf. Objects too massive to be considered planets, but not massive enough to sustain nuclear fusion like true stars. With a mass about 27 times that of Jupiter, Kelt 1b orbits remarkably close to its host star, completing an orbit in just 29 hours. This proximity creates an intensely hot environment, with temperatures reaching approximately 4,300 degrees Fahrenheit, 2,400 degrees Celsius. What makes Kelt 1b particularly interesting is its relationship with its host star. The brown dwarf orbits a star slightly larger and hotter than our Sun, but at such a close distance that it experiences extreme tidal forces. These forces have likely locked Kelt 1b's rotation, meaning one side perpetually faces its star while the other remains in darkness. The day side of Kelt 1b would be a hellish environment of extreme heat, where most materials would exist in gaseous form. The atmosphere would be a turbulent mix of vaporized metals and minerals, constantly churning under the influence of intense radiation from the nearby star. The night side, while still incredibly hot by Earth standards, would be significantly cooler than the day side. This temperature differential would generate ferocious winds as heat is redistributed around the brown dwarf, creating a perpetual global storm system unlike anything in our solar system. Scientists are particularly interested in Kelt 1b because it helps define the boundary between massive planets and failed stars. Its study provides insights into both planetary and stellar formation processes, occupying a unique position in our understanding of cosmic objects. GJ 504b, the pink gas giant. From scorching heat, we move to a world of unexpected color. GJ 504b, located about 57 light-years from Earth, is one of the most visually striking planets ever discovered, a gas giant with a distinctive pink hue. This distant world orbits the star GJ 504, which is slightly hotter than our Sun and visible to the naked eye in the constellation Virgo. Unlike the hot Jupiters we've discussed, GJ 504b orbits at a considerable distance from its star, about 43 astronomical units, similar to Pluto's distance from our Sun. Despite this distance, GJ 504b is remarkably warm, with a temperature of about 460 degrees Fahrenheit, 237 degrees Celsius. This unexpected heat is likely due to the planet's youth, estimated to be only about 160 million years old. It still retains significant heat from its formation. The most fascinating aspect of GJ 504b is its color. Most gas giants appear in shades of blue, brown, or yellow, but this world glows with a distinct magenta or pink hue. Scientists believe this coloration comes from its cloud composition and the way its atmosphere scatters light. The planet's mass is estimated at about 4 times that of Jupiter, placing it at the upper range of planetary masses. Some scientists have suggested it might actually be a brown dwarf rather than a planet, highlighting the sometimes blurry line between these cosmic categories. If you could somehow visit this distant pink world, you would find yourself approaching a strikingly colorful sphere set against the blackness of space. The atmosphere would consist primarily of hydrogen and helium, but with complex cloud layers containing various compounds that contribute to its unusual coloration. The study of GJ 504b is particularly valuable because it was one of the first exoplanets to be directly imaged, rather than detected through indirect methods. This direct observation allows astronomers to study its atmospheric composition in greater detail than is possible for most exoplanets. OGLE 2000 5BLG 390 LB. The frozen super-Earth. Our journey through temperature extremes now takes us to one of the coldest known exoplanets, OGLE 2000 5BLG 390 LB, sometimes nicknamed Hoth, after the ice planet in Star Wars. This super-Earth orbits a red dwarf star approximately 21,500 light-years from Earth, near the center of our Milky Way galaxy. What makes this world remarkable is its extreme cold, with surface temperatures estimated at about -364 degrees Fahrenheit, -220 degrees Celsius. It is one of the most frigid planets ever discovered. This intense cold results from its distance from its faint host star. It orbits at about 2.6 astronomical units, similar to the asteroid belt in our solar system. Ogle 2005 BLG 390 LB has a mass approximately 5.5 times that of Earth and is likely a rocky world rather than a gas giant. Under such extreme cold, the surface would be permanently frozen, with common gases like nitrogen, oxygen, and carbon dioxide existing as solid ice rather than in gaseous form. The discovery of this frozen super-Earth was particularly significant because it was found using gravitational microlensing, a technique that detects planets through the way their gravity bends light from background stars. This method allows astronomers to find planets at greater distances than other techniques, expanding our census of worlds throughout the galaxy. If you could stand on the surface of this frozen world, you would find yourself in a landscape of exotic ices. Water ice would be as hard as steel. Nitrogen and methane would form strange, brittle formations across the surface. The sky would be dominated by stars, with the host star appearing as little more than a bright point of light, providing minimal illumination to the frozen landscape below. Any movement on such a world would be challenging, as materials we consider flexible on Earth would become brittle in the extreme cold. The very atmosphere, if any remained, would be still, as there would be minimal energy to drive weather patterns. It represents a world locked in eternal winter, a testament to the extreme environments that can exist even on rocky planets. The lava ocean world. Returning to the realm of extreme heat, we encounter Co-Rho T7b, one of the first rocky super-Earths discovered outside our solar system. Located about 489 light-years from Earth, this world represents one of the most hostile environments ever identified. Co-Rho T7b orbits extraordinarily close to its star, completing an orbit in just 20.4 hours. This proximity creates a surface temperature on the dayside estimated at about 4220 degrees Fahrenheit, 2327 degrees Celsius, hot enough to vaporize rock and create oceans of molten lava. With a radius about 1.58 times that of Earth and a mass approximately 7.3 times greater, Co-Rho T7b falls squarely into the super-Earth category. Its density suggests a composition similar to Earth's, primarily silicate rocks and metals. But unlike Earth, the extreme conditions have created an environment utterly hostile to life as we know it. The planet is almost certainly tidally locked, with one side perpetually facing its star. This creates a stark division between hemispheres. The day side would feature a surface of molten rock, with certain minerals existing as vapor in the thin atmosphere. Silicon-based compounds might evaporate from the hottest regions, condense in slightly cooler areas, and then rain back onto the molten surface in a continuous cycle. The night side, while significantly cooler, would still be extremely hot by Earth standards. The temperature gradient between hemispheres would create powerful winds, potentially carrying vaporized rock from the day side to condense, and snow onto the night side in a bizarre weather pattern of rocky precipitation. The discovery of Co-Rho T7b was groundbreaking because it provided the first clear evidence that rocky planets could exist in extremely close orbits around their stars, a configuration not seen in our solar system. It expanded our understanding of the diversity of planetary systems and the extreme conditions under which rocky worlds can form and persist. If you could somehow observe this world from a safe distance, you would witness a planet with a glowing hot day side, potentially emitting its own visible light from the intensity of its heat. The boundary between day and night would feature spectacular storms as superheated materials circulate between the hemispheres in a perpetual cycle of vaporization and condensation. Additional content. Bizarre atmospheric planets. HAT P11b, the Neptune with water vapor. Our exploration of bizarre atmospheres continues with HAT P11b, a Neptune-sized exoplanet located approximately 124 light-years from Earth in the constellation Cygnus. This world has provided astronomers with one of the clearest detections of water vapor in an exoplanet atmosphere. HAT P11b orbits its star every 4.9 days and has a mass about 26 times that of Earth. Unlike the hot Jupiters we've discussed, this planet falls into the category of hot Neptune. Similar in size to Neptune in our solar system, but orbiting much closer to its star. What makes HAT P11b's atmosphere particularly interesting is its clarity. Many hot Jupiters and Neptunes have atmospheres obscured by high-altitude clouds or hazes, making detailed composition studies difficult. But HAT P11b has a remarkably clear upper atmosphere, allowing astronomers to detect the unmistakable signature of water vapor. The presence of water in its atmosphere doesn't mean HAT P11b is habitable with temperatures around 1120 degrees Fahrenheit, 600 degrees Celsius. The water exists only as vapor, not liquid. However, the detection is significant because water is a key molecule for life, as we know it. And understanding its distribution in planetary atmospheres helps us assess the potential habitability of worlds beyond our solar system. The atmosphere of HAT P11b likely consists primarily of hydrogen and helium, like our own ice giants Neptune and Uranus. But the water vapor content is substantial, suggesting the planet formed farther from its star where water ice was abundant, and then migrated inward to its current close orbit. If you could observe this world up close, you would see a blue-hued planet with a thick, dynamic atmosphere. Powerful winds would circulate around the planet, driven by the intense heat from its star. The water vapor in its upper atmosphere would interact with stellar radiation, potentially creating unique cloud formations, unlike anything in our solar system. The study of HAT P11b represents an important step in our ability to characterize exoplanet atmospheres. As our observational techniques improve, we're increasingly able to determine not just the size and orbit of distant worlds, but also their atmospheric composition, bringing us closer to understanding the true diversity of planets throughout our galaxy. WASP 121b, the planet with a stratosphere. Our next atmospheric wonder is WASP 121b, a hot Jupiter located about 880 light-years from Earth that has provided astronomers with the first clear evidence of a stratosphere on an exoplanet. Just as Earth's atmosphere has layers with different temperature profiles, this distant world shows a similar structure, but with extreme differences. WASP 121b orbits extremely close to its star, completing an orbit in just 1.3 days. This proximity heats the planet to temperatures around 4,600 degrees Fahrenheit, 2,500 degrees Celsius. The planet is so close to its star that it has an egg-shaped rather than spherical form, distorted by intense gravitational forces. What makes WASP 121b's atmosphere truly remarkable is its temperature structure. In Earth's atmosphere, the troposphere lowest layer gets colder with increasing altitude, while the stratosphere above it gets warmer with altitude due to ozone absorbing ultraviolet radiation. Astronomers discovered that WASP 121b shows a similar pattern. Its upper atmosphere gets hotter rather than colder with increasing altitude. This temperature inversion is caused by the presence of vanadium oxide and titanium oxide in the planet's atmosphere. These compounds absorb starlight at visible wavelengths, heating the upper atmosphere in a process somewhat similar to how ozone warms Earth's stratosphere. The stratosphere of WASP 121b is extraordinarily hot, with temperatures increasing by thousands of degrees at higher altitudes. This creates conditions where water molecules can be torn apart into their constituent hydrogen and oxygen atoms, a process called dissociation that occurs only under extreme heat. If you could somehow observe this world up close, you would see a planet with a glowing, dynamic atmosphere. The boundary between its troposphere and stratosphere would likely feature dramatic cloud formations and weather patterns driven by the extreme temperature differentials. The upper atmosphere might glow with a distinctive hue created by the presence of vaporized metals and unusual compounds. The discovery of a stratosphere on WASP 121b is significant because it demonstrates that the same basic atmospheric physics that operate on Earth can also function on worlds with radically different compositions and temperature regimes. It's a reminder that despite the alien nature of these distant planets, they are governed by the same fundamental physical laws that shape our own world. GJ 1214b, the water-rich super-Earth with a steamy atmosphere. Returning to GJ 1214b for a more detailed exploration. This super-Earth represents one of the most intriguing atmospheric mysteries in exoplanet science. Located just 40 light-years from Earth, it's close enough for detailed study, yet its atmosphere has proven remarkably difficult to characterize definitively. GJ 1214b orbits a red dwarf star every 1.6 days and has a radius about 2.7 times that of Earth. Its mass is approximately 6.5 times Earth's, giving it a density that suggests a composition significantly different from our rocky home world. The leading theory is that GJ 1214b contains substantial amounts of water, perhaps 50% or more of its total mass. The atmosphere of this world has been the subject of intense study and debate. Initial observations showed a remarkably featureless spectrum, suggesting either a clear atmosphere composed primarily of hydrogen and helium, or a thick layer of high-altitude clouds or haze obscuring the view of lower atmospheric layers. More recent studies favor the second explanation. GJ 1214b appears to be shrouded in thick clouds unlike any in our solar system. These clouds might be composed of potassium chloride or zinc sulfide particles, creating a perpetual global haze layer high in the atmosphere. Below these clouds, the atmosphere is likely rich in water vapor. At the temperatures present on GJ 1214b, around 450 to 550 degrees Fahrenheit, or 230 to 290 degrees Celsius, water would exist primarily as a supercritical fluid or vapor rather than liquid. The interior structure of GJ 1214b presents another fascinating possibility. Under its thick atmosphere likely lies a global ocean, but not of liquid water as we know it on Earth. Instead, this would be an ocean of exotic water phases that exist under extreme pressure forms like hot ice, that remain solid despite high temperatures due to the immense pressure. If you could somehow descend through the atmosphere of GJ 1214b, you would first encounter the high-altitude haze layer, obscuring your view in all directions. As you move deeper, the atmosphere would become increasingly dense and hot. Eventually, you might reach a boundary that isn't clearly liquid or gas, but a supercritical state where the distinction between ocean and atmosphere blurs. The study of GJ 1214b is particularly valuable because it represents a type of planet completely absent from our solar system, a water world, with a composition between that of Earth and Neptune. Understanding such worlds helps fill a crucial gap in our knowledge of planetary formation and evolution. HD 209458b, the evaporating planet. Our final additional atmospheric wonder is HD 209458b, nicknamed Osiris, a hot Jupiter located about 150 light-years from Earth that is literally evaporating before our eyes. This planet holds a special place in exoplanet science as the first transiting planet discovered and the first exoplanet found to have an atmosphere. HD 209458b orbits extremely close to its star, completing an orbit in just 3.5 days. This proximity heats the planet to temperatures around 2,000 degrees Fahrenheit, 1,100 degrees Celsius. The intense radiation from its star is causing the planet's upper atmosphere to expand and escape into space. Observations using the Hubble Space Telescope revealed something remarkable. HD 209458b is surrounded by an enormous cloud of hydrogen that extends far beyond the planet itself. This hydrogen is being stripped away from the planet by stellar radiation, creating a tail similar to that of a comet that trails behind the planet as it orbits. The rate of atmospheric loss is substantial, estimated at about 10,000 tons of material per second. Despite this seemingly dramatic figure, the planet is so massive that this process would only reduce its mass by about 0.1% over its entire lifetime. So there's no danger of the planet completely evaporating. The composition of HD 209,458b's atmosphere has been studied in greater detail than almost any other exoplanet. In addition to hydrogen, astronomers have detected sodium, oxygen, carbon, and even water vapor. The presence of these heavier elements in the extended atmosphere suggests powerful upwelling processes that carry material from deeper atmospheric layers. Perhaps most intriguingly, the planet's atmosphere shows evidence of high-speed winds that circle the planet at rates of up to 5,000 miles per hour. These winds help redistribute heat from the day side to the night side, creating a complex global weather system. If you could observe HD 209,458b up close, you would see a planet surrounded by an enormous glowing cloud of hydrogen that extends far into space. This cloud would be constantly replenished as more atmospheric material escapes the planet's gravity, creating a dynamic, ever-changing envelope around the world itself. The study of HD 209,458b has been pivotal in developing our techniques for atmospheric characterization of exoplanets. As one of the brightest and most accessible transiting planets, it has served as a testbed for methods now being applied to a wide range of exoplanets, helping us build a more comprehensive picture of atmospheric diversity throughout our galaxy. Additional content: strange composition worlds, Kepler 36b and c, the mismatched neighbors. Our exploration of strange compositions continues with one of the most puzzling planetary pairs ever discovered. Kepler 36b and Kepler 36c orbit the same star at nearly identical distances, but have radically different compositions, a configuration that challenges our understanding of planetary formation. Located about 1,200 light-years from Earth, these two worlds orbit their star with periods of 13.8 and 16.2 days, respectively. What makes this system extraordinary is how close these planets come to each other. At their nearest approach, they are separated by only about 1.2 million miles, just 5 times the Earth-Moon distance. This is the closest regularly approaching pair of planets known. Despite their proximity to each other, these worlds could hardly be more different in composition. Kepler 36b is a rocky super-Earth with a radius about 1.5 times that of Earth, and a density suggesting a composition similar to our world, primarily silicate rocks and metals. Kepler 36c, by contrast, is a Neptune-like world with a radius 3.7 times that of Earth and a much lower density, indicating a substantial envelope of hydrogen and helium surrounding a smaller rocky or icy core. This stark compositional difference between planets in such similar orbits presents a profound puzzle for planetary formation theories. Typically, planets that form at similar distances from their star should have access to similar building materials and thus develop comparable compositions. The Kepler 36 system seems to defy this expectation. Scientists have proposed several explanations for this unusual pairing. Perhaps the planets formed at different distances and later migrated to their current positions. Or maybe Kepler 36b once had a substantial gaseous envelope like its neighbor, but lost it through some catastrophic process like a massive impact or intense stellar radiation. If you could observe this system from one of these worlds, you would witness something remarkable. When Kepler 36b and c make their closest approach, each would appear larger in the other's sky than the Moon appears from Earth. An observer on the rocky Kepler 36b would see the gas-rich Kepler 36c as an enormous disk dominating the sky, appearing about 2.5 times larger than our full Moon. The gravitational interactions between these worlds would be substantial, creating powerful tidal forces that might drive volcanic activity on the rocky planet and atmospheric dynamics on the gaseous one. Their mutual gravitational dance would also cause significant variations in their orbits over time, creating a complex, ever-evolving system. The Kepler 36 system reminds us that planetary systems can develop in ways that challenge our expectations, with worlds of radically different compositions existing side by side. It's a humbling reminder of how much we still have to learn about the processes that shape planets throughout our galaxy. K2 to 18b. The Hycean world. Our next unusual composition belongs to K2 to 18b, a world that represents an entirely new category of potentially habitable planets, called Hycean worlds, planets with hydrogen-rich atmospheres and ocean-covered surfaces that could potentially support life. Located about 124 light-years from Earth, K2 to 18b orbits a cool red dwarf star within its habitable zone, completing an orbit every 33 days. With a radius about 2.6 times that of Earth and a mass approximately 8.6 times greater, it falls into the category of mini-Neptune, larger than Earth, but smaller than Neptune in our solar system. What makes K2 to 18b particularly intriguing is the detection of water vapor, methane, and potentially carbon dioxide in its atmosphere. These compounds are all considered potential biosignatures molecules that could indicate the presence of life. The composition of K2 to 18b likely includes a rocky core surrounded by a deep ocean of water, with a thick hydrogen-rich atmosphere above. This configuration has led scientists to classify it as a potential Hycean world, a term combining hydrogen and ocean. Hycean worlds represent an exciting new frontier in the search for habitable environments. While they differ significantly from Earth, with much thicker atmospheres and higher pressures, they could still potentially support microbial life. The temperature at the boundary between the ocean and atmosphere on K2 to 18b is estimated to be between 0 and 40 degrees Celsius, well within the range where life as we know it could exist. If you could somehow descend through the atmosphere of K2 to 18b, you would first encounter a thick layer of hydrogen and helium, mixed with water vapor and other compounds. As you moved deeper, pressure and temperature would increase. Eventually, you might reach a boundary where the atmosphere transitions to a global ocean, not of liquid water as we know it on Earth, but potentially a more exotic form existing under higher pressure and temperature. The discovery of methane in K2 to 18b's atmosphere is particularly significant. On Earth, most atmospheric methane is produced by living organisms. While there are non-biological processes that can also generate methane, its presence alongside water vapor makes this world a prime target in the search for life beyond our solar system. K2 to 18b challenges our Earth-centric view of habitability, suggesting that life might exist in environments quite different from our home world. As we continue to study this and similar planets, we may need to expand our definition of what constitutes a potentially habitable environment. HD 130 1399 OB, the triple star planet. Our exploration of strange compositions now takes us to HD 130 1399 OB, a world with one of the most unusual stellar environments ever discovered. Located about 340 light-years from Earth in the constellation Centaurus, this planet orbits in a system with not one, not two, but three stars. HD 130 1399 OB is a gas giant about 4 times the mass of Jupiter, with a composition likely similar to the gas giants in our solar system, primarily hydrogen and helium, with traces of methane, ammonia, and other compounds. What makes this world truly remarkable is not its composition, but the stellar system it inhabits. The planet orbits the largest of the three stars, HD 130 1399a, which is about 80% more massive than our Sun. The other two stars, HD 130 1399b and c, are smaller and orbit each other as a close binary pair. This binary pair, in turn, orbits at a greater distance from star A. The orbit of HD 130 1399 OB places it in an extraordinarily complex gravitational environment. It completes an orbit around star every 550 Earth years, while the binary pair B and C orbit A every 3,500 years. This configuration places the planet near the limit of orbital stability, any farther from its host star, and the gravitational influence of the binary pair would likely disrupt its orbit. This unusual arrangement creates a world with a truly alien sky. For about half of the planet's year, all three stars would be visible simultaneously, creating a landscape that never experiences true night. During this period, an observer on the planet would see the primary star dominating the sky, while the binary pair B and C would appear as a bright, double point of light that gradually moves across the background. For the other half of its year, the planet would be positioned such that the binary pair would set as the primary star rises, and vice versa. This would create a brief period of twilight rather than complete darkness, a world where three suns create an environment of perpetual day or near day. The discovery of HD 131,399 Ob challenges our understanding of how planets form and evolve in multiple star systems. Traditional models suggested that the complex gravitational environment of triple star systems would prevent planets from forming or maintaining stable orbits at the distance observed. Yet here is a world that defies those expectations, suggesting that planets can form and persist in a wider range of environments than previously thought. If you could somehow visit this distant world, you would find yourself on a gas giant with no solid surface, floating in an atmosphere that gradually increases in pressure and temperature as you descend. But the most spectacular feature would be the sky above, where three suns create lighting conditions and celestial displays unlike anything experienced on Earth. Methuselah, the ancient planet, our final additional strange composition world, is officially designated PSR B1620-26b, but is more commonly known by its nickname, Methuselah. This planet earns its biblical name by being one of the oldest known planets in the universe, estimated to be about 12.7 billion years old, nearly 3 times the age of our Earth, and almost as old as the universe itself. Located about 12,400 light-years from Earth in the globular cluster M4, Methuselah orbits an extraordinary pair of stars. A pulsar, the ultradense remnant of a massive star that exploded as a supernova, and a white dwarf, the remnant of a sun-like star that has exhausted its nuclear fuel. This unusual binary system provides clues to the planet's ancient origin. Methuselah is a gas giant with a mass about 2.5 times that of Jupiter. Its composition is likely similar to Jupiter, primarily hydrogen and helium, but with potentially significant differences reflecting its formation in the early universe. When Methuselah formed, the universe contained far fewer heavy elements than it does today, as these are created inside stars and distributed when those stars die. This ancient origin makes Methuselah a first-generation planet, formed when the universe was just 1 to 2 billion years old. Its existence challenges earlier theories that suggested planets couldn't form, until the universe had been enriched with heavier elements from multiple generations of stars. The history of the Methuselah system is a cosmic saga spanning billions of years. Scientists believe it began as a binary star system within the globular cluster. The more massive star evolved faster, eventually exploding as a supernova and leaving behind the pulsar we see today. Later, the second star evolved into a white dwarf. Throughout these violent stellar transformations, the planet somehow survived, maintaining its orbit around the binary pair. If you could visit this ancient world, you would find yourself approaching a gas giant that formed when the universe was in its infancy. The sky would be dominated by the dense star field of the globular cluster, with thousands of stars visible simultaneously. The binary system at the center would create an unusual lighting pattern, the white dwarf providing continuous illumination while the pulsar emits regular, intense pulses of radiation as it rotates. Methuselah serves as a cosmic time capsule, preserving information about planetary formation from the early universe. Its study helps us understand how quickly planets began to form after the Big Bang, and how the process of planetary formation has evolved over cosmic time. It's a reminder that the history of planets in our universe extends far beyond the relatively recent formation of our own solar system. Additional content: unusual orbit and rotation planets. Kepler 413b, the wobbling planet. Our exploration of unusual orbits continues with Kepler 413b, a planet that quite literally wobbles its way around its host stars. Located about 2,300 light-years from Earth in the constellation Cygnus, this world exhibits one of the strangest orbital behaviors ever observed. Kepler 413b is a gas giant about 65% the mass of Jupiter that orbits a close binary star system consisting of an orange dwarf and a red dwarf. It completes an orbit around both stars every 66 days. What makes this planet truly remarkable is the severe tilt and precession of its orbit. Most planets in our solar system orbit in a relatively flat plane, with orbital tilts of just a few degrees. Kepler 413b, by contrast, has an orbital tilt that changes by as much as 30 degrees over a period of 11 years. This means the planet's orbit wobbles up and down dramatically as it circles its host stars. This wobbling has a fascinating consequence for observers on Earth. Kepler 413b was discovered using the transit method, which detects planets when they pass in front of their stars from our perspective. But because of its wobbling orbit, Kepler 413b doesn't transit its stars during every orbit. Instead, it moves above or below the stars from our line of sight for years at a time, with transits occurring in clusters separated by long gaps. Scientists believe this unusual orbital behavior is caused by the gravitational influence of the binary star system. The complex gravitational field created by two stars orbiting each other can cause a planet's orbit to precess, or change orientation, much more dramatically than would occur in a single star system. If you could somehow visit this wobbling world, you would experience a constantly changing view of the binary stars. Over the course of the 11-year precession cycle, the apparent path of the stars across the sky would shift dramatically. Sometimes they would pass directly overhead, while at other times they would remain closer to the horizon. This would create seasons unlike anything on Earth, with periods of intense heating alternating with cooler periods as the planet's orientation to its stars changes. The discovery of Kepler 413b reminds us that planetary orbits need not be as stable and predictable as those in our solar system. In the complex gravitational environments created by binary stars, planets can follow paths that would seem impossible based solely on our local experience. Kepler 1647b, the massive circumbinary. Our next unusual orbit belongs to Kepler 1647b, a planet that holds several distinctions in the exoplanet catalog. Located about 3,700 light-years from Earth, it is one of the largest circumbinary planets ever discovered, planets that orbit both stars in a binary system. With a mass similar to Jupiter, but an orbit comparable in size to Earth's. Kepler 1647b orbits a binary system consisting of two stars similar to our Sun. It takes 1107 days, just over 3 Earth years, to complete one orbit around both stars. This places it much farther from its host stars than most known circumbinary planets, which typically orbit much closer to their stellar hosts. What makes Kepler 1647b's orbit particularly interesting is its size relative to the critical stability radius of the system. In binary star systems, there's a minimum distance at which planetary orbits become stable. Kepler 1647b orbits at about 3 times this critical distance, giving it one of the widest stable orbits known for a circumbinary planet. The planet follows a slightly eccentric path, meaning its distance from the central stars varies throughout its orbit. This eccentricity, combined with the changing positions of the two stars, creates a complex pattern of stellar heating. The amount of light and heat the planet receives would vary not just with its distance from the stars, but also with the constantly changing configuration of the binary pair. If you could observe this system from the planet, you would witness an extraordinary celestial dance. The two sun-like stars would orbit each other every 11.2 days, sometimes appearing close together in the sky, other times on opposite sides of the horizon. Eclipses would occur regularly as the stars pass in front of each other from the planet's perspective. The relatively large orbit of Kepler 1647b means it receives about the same amount of energy from its stars as Earth does from the Sun, despite the binary system being somewhat more luminous than our star. This places the planet near the outer edge of the system's habitable zone, the region where temperatures might allow liquid water to exist on the surface of a rocky world. While Kepler 1647b itself is a gas giant unlikely to harbor Earth-like life, it raises the intriguing possibility that it might host large moons with conditions more conducive to life. Such moons, if they exist, would experience not only the day-night cycle from their own rotation, but also complex patterns of illumination from the binary stars their planet orbits. The discovery of Kepler 1647b demonstrates that large planets can form and maintain stable orbits, even in the complex gravitational environment of binary star systems. It expands our understanding of where planets can exist and the diverse configurations planetary systems can take throughout our galaxy. HD 20782b, the most eccentric orbit. Our exploration of unusual orbits now takes us to HD 20782b, a planet that holds the record for the most eccentric orbit of any known exoplanet. Located about 117 light-years from Earth, this world follows a path more like that of a comet than a typical planet. HD 20782b is a gas giant with a mass at least 1.9 times that of Jupiter. It orbits a sun-like star with an orbital period of about 597 days. What makes this world truly extraordinary is the shape of its orbit, which has an eccentricity of 0.97, extremely close to the theoretical maximum of 1.0 that would represent a parabolic escape trajectory. This extreme eccentricity means that the planet's distance from its star varies dramatically throughout its orbit. At its farthest point, a pastron, it is about 2.5 astronomical units from its star, a distance similar to the asteroid belt in our solar system. But at its closest approach, periastron, it dives to just 0.06 astronomical units, closer than Mercury's orbit around our Sun. This cosmic roller coaster creates extreme variations in the amount of light and heat the planet receives. At periastron, it is bathed in about 1,000 times more stellar radiation than at a pastron. This would cause temperature swings of thousands of degrees over the course of its orbit. Scientists are still debating what could have created such an extreme orbit. One possibility is a close encounter with another massive planet that was ejected from the system. Another is the gravitational influence of a distant stellar companion orbiting the same star. If you could somehow observe HD 20782b throughout its orbit, you would see it spending most of its time in the outer reaches of its solar system, moving relatively slowly. Then, as it begins to fall toward its star, it would accelerate dramatically, whipping around the star in a brief, violent periastron passage before being flung outward again to begin the cycle anew. During its closest approach, the planet would likely experience dramatic atmospheric effects. The sudden intense heating could cause some atmospheric gases to expand rapidly or even be stripped away by stellar radiation. The side facing the star would be subjected to extreme temperatures, creating powerful winds as heat is redistributed around the planet. HD 20782b challenges our understanding of how planetary systems form and evolve. Traditional models of planet formation favor nearly circular orbits, as planets emerge from circular protoplanetary disks. The existence of planets with such extreme eccentricities suggests that disruptive events after formation, like gravitational interactions with other planets or passing stars, play a significant role in shaping the final architecture of planetary systems. Kepler 78b, the impossibly close planet. Our final additional unusual orbit belongs to Kepler 78b, a world that, according to our current understanding of planetary formation, shouldn't exist where it does. Located about 400 light-years from Earth, this Earth-sized planet orbits so close to its star that it completes a full orbit in just 8.5 hours, one of the shortest years of any known planet. Kepler 78b has a radius about 1.2 times that of Earth and a mass about 1.7 times greater. This gives it a density similar to our planet, suggesting a composition of rock and iron. What makes its orbit so puzzling is its proximity to its host star. It orbits at a distance of just 900,000 miles, about 1% of the Earth-Sun distance. At this incredibly close range, the planet is subjected to extreme conditions. Its surface temperature is estimated to be between 2,400 and 3,100 degrees Fahrenheit, 1,300 to 1,700 degrees Celsius, hot enough to melt rock and vaporize metals. The star's gravity also creates intense tidal forces that likely lock the planet's rotation, keeping one side perpetually facing the star. The mystery of Kepler 78b lies in its formation. According to current models, this planet orbits too close to its star to have formed in its current location. When the star was younger, it would have been larger, extending beyond the planet's current orbit. This suggests that Kepler 78b must have formed farther out and somehow migrated inward. However, standard migration mechanisms typically don't bring planets quite this close to their stars. Scientists are still debating how Kepler 78b arrived at its current position, with some suggesting novel migration processes, or even the possibility that the planet is the exposed core of a once larger world that lost its outer layers to stellar radiation. Whatever its origin, Kepler 78b's fate seems clear. It orbits so close to its star that it experiences strong tidal forces that are gradually causing it to spiral inward. Within a few billion years, it will likely be consumed by its star, a cosmic fate that awaits many planets in ultra-short orbits. If you could somehow observe this world up close, you would see a rocky planet with a surface of molten rock, potentially with a thin atmosphere of vaporized minerals. The star would dominate the sky from the dayside, appearing about 80 times larger than the Sun appears from Earth. The heat would be intense enough to vaporize most materials, creating an environment more like the surface of a star than a planet as we typically understand them. Kepler 78b represents an extreme case of planetary orbits, showing us that planets can exist in configurations that challenge our theoretical understanding. Its study helps refine our models of how planets form, migrate, and eventually meet their end in the complex dance of stellar systems. Additional content: potentially habitable strange worlds. LHS 1140b. The dense super-Earth. Our exploration of potentially habitable strange worlds continues with LHS 1140b, a super-Earth located just 49 light-years from our solar system. This proximity makes it one of the closest potentially habitable exoplanets and an excellent target for detailed study with current and future telescopes. LHS 1140b orbits a red dwarf star significantly smaller and cooler than our Sun. It completes an orbit every 24.7 days, placing it within the star's habitable zone, the region where temperatures might allow liquid water to exist on the surface. What makes LHS 1140b particularly interesting is its density. With a radius about 1.7 times that of Earth, but a mass approximately 6.7 times greater, it is significantly denser than our planet. This high density suggests a composition dominated by rock and metal, possibly with a large iron core similar to Earth's, but proportionally larger. The planet's high mass would create a surface gravity about twice that of Earth. This stronger gravity would help the planet retain its atmosphere against the radiation from its host star, a significant advantage for habitability around red dwarfs, which are known for their energetic flares. LHS 1140b orbits a star estimated to be about 5 billion years older than our Sun. This extended age means the star has likely settled into a more stable phase, with fewer of the violent flares that characterize younger red dwarfs. This stellar maturity improves the prospects for long-term habitability. If you could stand on the surface of LHS 1140b, you would feel the stronger gravity making every movement more effortful. The red dwarf star would appear larger in the sky than our Sun appears from Earth, but would glow with a dimmer, reddish light. The overall illumination would be less intense than on Earth, giving the landscape a perpetual twilight quality. The planet is likely tidally locked, with one side always facing its star. This would create stark environmental differences between hemispheres, a perpetually lit day side and a dark night side. However, with a substantial atmosphere, heat could be distributed around the planet, potentially creating a habitable zone along the terminator line where day meets night. One of the most intriguing aspects of LHS 1140b is that its star is small enough, and the planet's orbit aligned such that it transits the star from our perspective. This alignment allows astronomers to study light passing through any atmosphere the planet might have, potentially revealing its composition and habitability. The combination of LHS 1140b's location within the habitable zone, its rocky composition, its substantial mass that can retain an atmosphere, and its orbit around a mature red dwarf makes it one of our most promising candidates for a potentially habitable world beyond our solar system. TOI 700e, the Goldilocks planet. Our next potentially habitable strange world is TOI 700e, the fourth planet discovered in the TOI 700 system, located about 100 light-years from Earth. This world holds special significance as one of the few Earth-sized planets discovered in the optimum part of its star's habitable zone. Not too hot, not too cold, but potentially just right for liquid water. TOI 700e has a radius about 95% that of Earth, making it almost exactly Earth-sized. It orbits a small, cool red dwarf star every 28 days, placing it comfortably within the star's habitable zone. In fact, it orbits in what astronomers sometimes call the optimistic habitable zone, a region where even a planet with a thin atmosphere might maintain surface temperatures suitable for liquid water. What makes the TOI 700 system particularly interesting for habitability studies is the star itself. Unlike many red dwarfs, TOI 700 appears to be relatively quiet, with fewer of the powerful flares that could strip away planetary atmospheres or bathe surfaces in harmful radiation. This stellar calm improves the prospects for long-term habitability. TOI 700e was discovered alongside its sibling planet TOI 700d, which we discussed earlier. Together, they form a pair of potentially habitable worlds orbiting the same star, one of the few such pairs known. This configuration raises intriguing possibilities about the potential for life to evolve independently on neighboring worlds, or perhaps even to transfer between them through a process called panspermia. If you could visit TOI 700e, you would find yourself on a world bathed in the reddish light of its host star. The star would appear larger in the sky than our Sun does from Earth, but would provide less overall illumination. The planet is likely tidally locked, creating a permanent day side and night side, with the most habitable conditions potentially existing along the boundary between them. The discovery of TOI 700e is particularly significant because it was found using NASA's TESS, Transiting Exoplanet Survey satellite mission, which is designed to find small planets around nearby stars. Its proximity to Earth makes it an excellent candidate for follow-up studies with the James Webb Space Telescope and other next-generation instruments, which may be able to characterize its atmosphere and assess its true habitability potential. As one of the most Earth-like planets discovered in the optimum habitable zone of its star, TOI 700e represents a prime target in our search for potentially habitable worlds beyond our solar system. Its study may provide crucial insights into whether planets around red dwarf stars, the most common type of star in our galaxy, could support life as we know it. Teegarden Star B. The nearby temperate world, our exploration of potentially habitable strange worlds, now takes us to one of the closest and most promising candidates for habitability beyond our solar system. Teegarden Star B orbits an ultra-cool red dwarf star just 12.5 light-years from Earth, making it one of our nearest exoplanetary neighbors. Teegarden Star B has a minimum mass of about 1.05 times that of Earth and orbits its star every 4.9 days. Despite this short orbital period, the planet receives about 87% of the energy that Earth receives from the Sun, placing it well within the star's habitable zone. What makes this world particularly interesting is its Earth Similarity Index, SE value of 0.95, on a scale where 1.0 would represent a perfect Earth twin. This high value, based on the planet's estimated mass, radius, and surface temperature, makes it one of the most Earth-like exoplanets discovered to date. Teegarden Star itself is an ancient red dwarf, estimated to be at least 8 billion years old. This advanced age means the star has likely settled into a stable phase, with fewer violent flares than younger red dwarfs, creating a more hospitable environment for potential life. The star is so small and cool that it emits most of its energy in the infrared rather than visible light. This means that if you could stand on the surface of Teegarden Star B, the landscape would be illuminated primarily by infrared radiation, with the star appearing as a dim, reddish point in the sky. Like many planets orbiting red dwarfs, Teegarden Star B is likely tidally locked, with one side perpetually facing its star. However, the relatively mild stellar radiation would create less extreme temperature differences between the day and night sides compared to planets orbiting more energetic stars. If photosynthetic life were to evolve on such a world, it would need to adapt to the infrared-rich, visible light-poor stellar spectrum. Plants might develop black or very dark pigmentation to absorb as much of the available light as possible, creating landscapes quite different from the green-dominated environments of Earth. The proximity of the Teegarden star system to Earth makes it an excellent target for future observations. Next-generation telescopes may be able to directly image the planet or study its atmosphere, potentially revealing whether this nearby world truly has conditions suitable for life as we know it. As one of our closest potentially habitable neighbors, Teegarden Star B represents not just a fascinating scientific target, but also a symbolic milestone in our search for other Earth-like worlds. Its discovery reminds us that potentially habitable planets may be more common in our cosmic neighborhood than previously thought. Kepler 1649c. The hidden Earth twin. Our final additional potentially habitable strange world is Kepler 1649c, a planet that remained hidden in data from the Kepler Space Telescope until a reanalysis in 2020 revealed its existence. Located about 300 light-years from Earth, this world is one of the most similar to our own in terms of both size and received stellar energy. Kepler 1649c has a radius about 1.06 times that of Earth, making it almost exactly Earth-sized. It orbits a red dwarf star every 19.5 days, receiving about 75% of the light that Earth receives from the Sun. This places it firmly within its star's habitable zone, where temperatures might allow liquid water to exist on the surface. What makes the discovery of Kepler 1649c particularly remarkable is how it was found. The planet was originally misclassified by the Kepler mission's automated processing system. Only when researchers manually reviewed the data did they recognize the signature of this Earth-sized world. This suggests that other similar planets might still be hiding in existing datasets, awaiting discovery. Like other planets orbiting red dwarfs, Kepler 1649c likely faces challenges to habitability. Its star is smaller and cooler than our Sun, emitting more of its energy as infrared radiation rather than visible light. The star is also prone to flares that could potentially strip away the planet's atmosphere or expose its surface to harmful radiation. Despite these challenges, Kepler 1649c remains one of our best candidates for an Earth analog beyond our solar system. Its size suggests it is likely rocky rather than gaseous, and its position in the habitable zone means it could potentially maintain surface temperatures suitable for liquid water, a key requirement for life as we know it. If you could visit this distant world, you would find yourself on a planet illuminated by the reddish light of its host star. The star would appear larger in the sky than our Sun does from Earth, but would provide less overall illumination. The landscape might be bathed in a perpetual twilight, with colors appearing muted or shifted compared to how they would look under our Sun. The planet is likely tidally locked, with one side always facing its star. This would create stark environmental differences between the perpetually lit day side and the dark night side. However, with a substantial atmosphere, heat could be distributed around the planet, potentially creating a band of habitable conditions along the terminator line where day meets night. The discovery of Kepler 1649c highlights the importance of careful data analysis in the search for potentially habitable worlds. It reminds us that significant discoveries can sometimes be overlooked in the vast amounts of data collected by our astronomical surveys, and that revisiting existing observations with new techniques or perspectives can yield remarkable findings. As one of the most Earth-like planets discovered to date in terms of both size and received stellar energy, Kepler 1649c represents a significant milestone in our quest to find worlds that might harbor life beyond our solar system. Philosophical reflections on cosmic diversity. As we near the conclusion of our journey through the strange worlds beyond our solar system, let us take a moment to reflect on the broader implications of the incredible diversity we've encountered. The discovery of thousands of exoplanets in just the past few decades has fundamentally transformed our understanding of our place in the universe. Where once we knew of only the planets in our own solar system, we now recognize that planetary systems are the norm rather than the exception, with most stars hosting their own families of worlds. More profound still is the realization of just how diverse these planetary systems can be. We've encountered hot Jupiters orbiting perilously close to their stars, super-Earths and mini-Neptunes with no analog in our solar system, and worlds with compositions, atmospheres, and orbital characteristics that would have seemed impossible based solely on our local experience. This diversity challenges us to reconsider what we consider normal in planetary formation and evolution. Our solar system, with its relatively orderly arrangement of inner rocky planets and outer gas giants, appears to be just one possibility among many. The universe has proven far more creative in its planetary architectures than our limited imagination might have supposed. Perhaps most humbling is the recognition that we've only begun to scratch the surface of this cosmic diversity. The planets we've discovered so far are biased toward those that are easier to detect with our current technology, large worlds close to their stars, or planets orbiting smaller, dimmer stars. As our observational capabilities improve, we can expect to discover even more variety in the planetary census. This expanding awareness of cosmic diversity extends to our search for life beyond Earth. We've traditionally focused on finding planets similar to our own rocky worlds at similar distances from sun-like stars. But the strange worlds we've explored suggest that habitability might exist across a much broader spectrum of planetary conditions than we initially imagined. From the potential water worlds with deep global oceans to the tidally locked planets with eternal twilight zones, from the super-Earths with stronger gravity to the worlds orbiting red dwarfs with their infrared-rich illumination. Each represents an environment where life might evolve along paths different from those taken on Earth. This possibility invites us to expand our imagination about what life might look like elsewhere in the universe. If life can adapt to the extreme environments found on Earth, from acid hot springs to Antarctic ice to the crushing depths of the ocean, might it not also adapt to the alien conditions on these strange, distant worlds? The diversity of exoplanets also raises profound questions about our own origins. Is our solar system typical or unusual? Did its particular configuration play a crucial role in the emergence of complex life on Earth? Or might life be equally likely to emerge in very different planetary systems? As we continue to explore these strange worlds beyond our solar system, we are not merely cataloging distant planets. We are piecing together a more complete understanding of our cosmic context, of the processes that shape planetary systems throughout the galaxy, and of the range of environments where life might potentially emerge. In this expanded cosmic perspective, Earth appears both more precious and less unique. More precious because we recognize more fully the specific combination of factors that make our home world so hospitable to complex life. Less unique because we see that many of Earth's individual characteristics, its rocky composition, its watery surface, its position in the habitable zone, are replicated on countless worlds throughout the galaxy. Perhaps the most profound implication of our exoplanet explorations is the recognition of our deep connection to this cosmic diversity. The elements that make up our bodies, the carbon, nitrogen, oxygen, and other atoms that combine to form our cells, were forged in ancient stars and distributed through space when those stars died. We are, in the most literal sense, made of stardust, connected through our very atomic composition to the strange worlds we've been exploring. As you drift toward sleep, consider that the same physical laws and chemical processes that shape these distant exoplanets also shaped our own world, and ultimately ourselves. In studying these strange worlds beyond our solar system, we are not merely looking outward into the cosmos. We are also, in a very real sense, looking inward at our own origins and nature. The universe, in all its strange and wonderful diversity, is not separate from us, but is the greater whole of which we are a part. As we continue to discover and characterize more exoplanets, we are gradually piecing together not just a catalog of distant worlds, but a more complete understanding of our own place in the cosmic story. As you drift among these strange worlds, may your dreams be as vast as the cosmos itself. Sleep well, cosmic traveler. Until our next journey among the stars, good night.